In this video, we're going to look at how to name some simple ionic, covalent, and organic compounds needed for a general chemistry class. Before starting this video, you should already be familiar with the setup of the periodic table and determining how to find the charge of any given element on the periodic table from the main group elements. So before we actually dive into naming, we have to understand chemical formulas. So a couple of different pieces of information here. First of all, what is the definition of a chemical formula? This is a set of chemical symbols showing the elements in a compound in their relative proportions. So if we take a look at water, for instance, one of the most well-known chemical formulas, which is H2O, what this means is that we have hydrogen and oxygen in our chemical, and we also have 2 hydrogen atoms for every 1 oxygen atom. So if there's only one of something, we usually don't write that one. The one is assumed because we just have the symbol written. There are 2 different kinds of chemical formulas, a molecular formula and an empirical formula. The molecular formula shows the exact number of atoms in a compound. For example, if we look at something like hydrogen peroxide is H2O2, which means that there are 2 hydrogens and 2 oxygens. But an empirical formula takes the molecular formula and it lowers it down into the most reduced whole number ratios. So looking at hydrogen peroxide again, since we have 2 of each, we can divide by 2, and our empirical formula in this case would just be HO. So everything is reduced down as far as possible. Now, in some cases, the empirical formula and the molecular formula are the same, but not always. So we need to be familiar with the idea of reducing. We're going to start off by looking at covalent compounds. And so before we actually get to naming them, we need to understand how covalent compounds are written and how to identify that something is covalent. A covalent compound is always going to be made up of non-metals. So that's one way that you can determine it is covalent. So how do we write a formula for a covalent compound? We look to the periodic table. So elements further left on the periodic table are written first. However, there is an exception, and the exception is for bromine, chlorine, or iodine with oxygen. So if we look on the periodic table, oxygen is further left than bromine, chlorine, or iodine, than those halogens. So we would expect for oxygen to be written first, but the halogen is actually written first. So instead of writing OCl, we would write ClO. The second step is that if we're dealing with elements in the same column, we write down the element further in the column. Again, this only counts if we're looking at 2 elements that are in the same column. Now that we know how we can write the formulas, we can get to naming. And in order to name, we're going to start by naming the first element. Then we can name the second element, but it is going to end in "ide", in IDE. The last thing you need to pay attention to is using a Greek prefix to denote the number of each element. So let's talk about what those Greek prefixes are. 1 is mono, 2 is di, 3 is tri, 4 is tetra, penta, hexa, hepta, octa, nona, and deca. And that takes us all the way from 1 to 10. So let's look at one of the most popular or most well-known covalent compounds, something like carbon dioxide. So we write that formula as CO2. So carbon is further to the left than oxygen, which is why it comes first. Now notice that we name it carbon dioxide, not monocarbon dioxide. So we ignore mono if it is for the first element. You want to ignore mono if it's only for the first element. So you might also be familiar with this deadly gas, CO, known as carbon monoxide. So the mono still has to go with the oxygen, but since carbon is the first element, we exclude the mono. But for anything else, we don't want to exclude from that first element. So if we have something like N2O3, we would call that dinitrogen trioxide. And there's our compound. So that's looking at covalent compounds. Now we're going to look at a more specific type of covalent compound, organics. This is not an extensive overview of organic compounds. There's a lot more to go into with organic chemistry, but we're just giving you the most simplistic types of compounds that you should be familiar with. The first type is called an alkane, and an alkane is made up solely of carbons and hydrogens. And you can see that they have the generic formula of CnH2n plus 2. So in our first example here, CH4, we have one carbon. So N equals 1, which is why H equals 4. So let's get to naming. When we're naming organic compounds, we name based on the number of carbons in the molecule. And so here, our numbering is a little bit different. So for Greek, we did mono, di, tri. For organic, we use meth for 1, eth for 2, prop for 3, bute for 4. And then as we continue on, it's the same as the Greek. So for our first example, CH4, there's only one carbon. So meth is our prefix. And then all alkanes end with ane, A-N-E, from the name. So this is methane. Our next one has 2 carbons, so it is ethane. The next one we have written here would be propane. Now we can take these alkanes and turn them into alcohols by adding in an oxygen. And so here we follow the same rules of meth, eth, prop, etc., but our ending instead of ane is anol. So our ending becomes anol. So methane becomes methanol. Ethane becomes ethanol. And propane would become propanol. And you can continue this all the way down. Butane would become butanol, etc. So those are our organic compounds. Now let's take a look at ionic compounds. For ionic compounds, when we're writing their chemical formulas, we have to pay attention to the charge of each ion. So for example, Let's say that you're making a compound that uses magnesium and nitrogen. Based on the periodic table, we know that magnesium as an ion exists as 2+, whereas nitrogen exists as 3-. So what we do is we take these charges and we do a cross multiplication, which means that we're going to multiply magnesium by 3 and multiply nitrogen by 2. And so the easy way to think of this is to just take those charges, the absolute value of them, cross them, and bring them down as subscripts. So this would be written as Mg3N2. One other important factor for ionic compounds is that we always want to write them in their empirical formulas. So we want it to be reduced down as far as possible. 3 and 2 is already reduced down as much as it can be in keeping whole numbers. So we're going to leave it as Mg3N2. But what about if we have something like calcium and oxygen? Calcium we know is a 2+, oxygen is a 2-. So in this case, if we were to do that cross multiplication and bring them down, it would become Ca2O2, which we can reduce into its empirical form of CaO. So usually when you have charges that are the same magnitude but opposite in sign, we can just cancel them out completely. And so you don't even have to work your way through to find the empirical formula. Now let's look at what if we have a polyatomic ion. So let's say we have sodium with phosphate. Sodium is a positive charge. Phosphate is one of the one of the polyatomic ions that you should have memorized as PO4 3-. So we do our cross, and we would end up with Na3PO4. But what if when we cross, we end up adding a subscript to a polyatomic ion? So let's look at something like magnesium and nitrate. So we said before, magnesium is going to be a 2+, and nitrate is NO3 with a -1 charge. So when we cross those over, we get Mg with a 1, and then nitrate needs to have a 2 added to it. But we can't just write 2. We can't have a subscript of a subscript. So what we do when we need to add a new subscript to a polyatomic ion is we put that polyatomic ion in parentheses. And then we can put our 2 as a subscript. And that shows the distributive factor of this new subscript. That 2 belongs to both the nitrogen and the oxygen. So lastly, we could have something with a transition metal, for instance. So maybe we have something like iron 3+. So for a transition metal, these have a variety of different charges. So you would have to be told that this is the iron 3+ cation. And then maybe that's with the nitride ion. So when we put these together, since they are the same magnitude, they're going to completely cancel out, and that's just going to give us Fen. So now that we have our chemical formulas, we can start naming. And in order to name a compound, we first have to understand how to name each individual type of ion. So we're going to start by looking at ionic compounds. We're going to start by looking at cations in ionic compounds. When we're naming cations, it's very straightforward. It's literally the name of the metal, because all metals are cations, plus the word cation. So if we were looking at Na+, we would literally call that the sodium cation. For transition metals, it's a little bit different because again, they can have a variety of charges. So we need to specify what the charge is. And we do that using Roman numerals in parentheses. So thinking back to what we used in our last slide, the iron 3+ ion, we would call that iron parentheses 3 in Roman numerals cation. So as a reminder of your Roman numerals, we have 1, 2, 3, 4, 5, 6, 7. And you shouldn't see anything higher than 7. As for anions, things are a little more complicated. For monatomic anions, monatomic meaning that there's just one element, for monatomic anions, we just change the ending to "ide." So it's usually the first syllable plus "ide." So oxygen becomes oxide, nitrogen becomes nitride, etc. For oxyanions, they're a little more complicated. We can have an ending of "ate." We can have an ending of "ite." And "ite" just means that there's one less oxygen than the "ate" form. We can have a hypo as a prefix. So hypo means there's one less than the "ite" form, or we could have the per prefix. And per means that there's one more oxygen than the "ate" format. If we add hydrogen to an oxyanion, then we're going to see that the name becomes hydrogen plus whatever the name of the ion is. And if we are dealing with two hydrogens, we would call it dihydrogen. Of the oxyanion. Now, in some cases, instead of seeing hydrogen plus the anion, like hydrogen carbonate, you might see something as bi. So bicarbonate means hydrogen carbonate. So those two are interchangeable. So to name a binary ionic compound, you put the cation name and the anion name together. When we're dealing with some other types of ionic compounds, like acids, our names change slightly. So an acid, you'll usually be able to recognize because it has a hydrogen at the start of the formula, and then it's hydrogen with an anion. So if you have hydrogen at the start, you know that it's an acid. If you're dealing with a binary acid, binary meaning that we have two elements, so hydrogen and one other element, we're going to use the prefix hydro. So for binary, we're going to start with hydro as our prefix. We're going to name the other element, and usually we name the anion in "ide, but we're going to change "ide" to "ic." So for instance, if we're looking at HCl, that's binary because it's hydrogen and chlorine. So we would start with hydro. Normally we would say that that's chloride, so it's going to become chloric. And then we just add the word acid at the end. So HCl is hydrochloric acid. Things get more complicated if we're dealing with an acid that contains a polyatomic ion. And that's where this second rule comes in. If a polyatomic ion ends in -ate, it will become -ic for the acid name. If it ends in -ite, it will become -us for the acid name. So in this case, it's not going to have a prefix. So if there's a polyatomic ion, a PAI, there is no prefix. You just go right into the name. So let's say we're looking at HClO3. That's hydrogen with the chlorate ion. So chlorate is going to turn to -ic. So we're going to say that this is called chloric acid. Ite turns to -us. So if we had hydrogen with the chlorite ion, that would be chlorous acid. And I remember ate goes to -ic and ite goes to -us because it sounds like a disease, atic-itis. The last kind of inorganic compound is a hydrate. And a hydrate is just a compound that has water in its chemical structure. So it's always going to be written as some ionic compound and then a dot with water. So you're going to name the ionic compound as you always would, but then you have water attached, which is covalent. So we use the Greek prefix to show the number of waters, and then we say hydrate at the end. So for example, if we have something like Na2SO4 dot 10H2O, we would start by naming the ionic portion as itself. So that would be sodium sulfate. Notice that when we're naming the ionic compound, we don't say disodium. We only use those Greek prefixes if we're dealing with something that's covalent, and this is not. So it's just sodium sulfate. And then we get to the covalent part, which is the water. So we're going to add in the Greek. For 10 is deca, and then hydrate. So this would be sodium sulfate decahydrate. So another thing for you to notice is that we have a polyatomic ion in this formula. The name of a polyatomic ion does not change. So it stays as sulfate. Whereas when we were looking at monatomic ions, we changed to -ide. We're not doing that here. So let's look at some practice problems. Let's name these compounds. And in order to do that, we can figure out, is it covalent, which we know is made up of nonmetals, or is it ionic, which is a metal and a nonmetal, or contains a polyatomic ion? So looking at our first example, we have P4S5. Ask yourself, is this ionic or covalent? And how do you know? You should say that it's covalent because it's made up of nonmetals. And we can determine that by looking at the periodic table. They're both on the right side, so they're both nonmetals, which means we're looking at a covalent compound, so we're going to use the covalent rules. Since there are 4 of the first element, we're going to say tetra, and then phosphorus. And in the second element, we have 5 of, so that's going to be penta. And that element is sulfur, but it's the second element, so it gets changed to sulfide. So first syllable, sulf, and then ide. So that's tetraphosphorus pentasulfide. So our next one, I want you to figure out, is it ionic or covalent, and then try naming it. So feel free to pause for each of these and try naming them, and then double check your work. So this next one is N2O3. This is covalent, again made up of non-metals. So this is going to be dinitrogen trioxide. For our next one, we have copper and chlorine. This has to be an ionic compound because it contains a metal, the copper. So we name the cation and then we name the anion. Well, this cation is a transition metal, which means that we need to figure out what the charge is. So we can kind of backtrack. In order to write the formula, we took the charges and crossed them down. So we can take the subscripts and cross them up to figure out what the charges were. So this 2 had to come from the copper. So we know that copper must have been a 2, and it had to be a positive charge because it's a metal, and all metals are cations. So we would call this copper with Roman numerals 2 chloride. For our next one, we ask, is it ionic or covalent? It's covalent, it's all nonmetals, so it's going to be chlorine dioxide. Next one, ionic or covalent? Well, we can see that it's all nonmetals, but there's something special here. There's a hydrogen out front, which tells us that this is an acid. So then we have to ask, okay, if it's an acid, is it binary or does it contain a polyatomic ion? And in this case, it contains a polyatomic ion. So we're going to look at the polyatomic ion, see that it is acetate. So 8 turns to ic. This is called acetic acid. For our next one, we can tell that this is ionic. Again, metal and non-metal. We can take these subscripts and backtrack them to find out that the iron is a 2+. So iron 2 nitride. Next one is covalent, sulfur hexafluoride. Next one is ionic, sodium oxide. And then our last one is a hydrate because we have that water. So we name the ionic compound magnesium sulfate. And then 7 is hept. So that would be heptahydrate. So again, I want you to notice that for ionic compounds, we are not using any Greek or anything to signify how many of each type of element we have. We only do that for covalent compounds. So let's do the same thing, but writing the formulas instead of the name. So again, take a second to pause the video, try this out yourself. So for this first one, we see a Greek prefix, penta. So that tells us that this is going to be covalent. So iodine comes first, I, and then 5 of fluorine, so IF5. Nitrogen tribromide, again, we have that tri, so we're going to put nitrogen first, then bromine, and we have 3 of them. Titanium 3 bromide, so that means we're looking at titanium, which is a 3+, it's a transition metal. Bromine, we can look on the periodic table and see that it's a -1, so this would be TiBr3. Magnesium phosphate. Magnesium we know is a 2+, phosphate is a 3-, so that becomes Mg3. PO4 2, and we need those parentheses because we're adding a new subscript to our polyatomic ion. Chromium 6 phosphide. So chromium, oops, not CH, Cr. Chromium is a 6 plus, phosphide is a 3 minus, so we put those together and we get Cr3 piece, but we're not done yet because we can reduce that down to its empirical formula. So it would be CrP2. Next we have copper 2 sulfate pentahydrate. So copper 2 is Cu2 plus, sulfate is SO4 2 minus. So we put those together, we get CuSO4 because they cancel out. Penta is 5, hydrate is water. Next we have silver acetate. Now this is a transition metal that you'll notice doesn't have any Roman numerals with it. And that's because it's special. So silver and zinc are two elements that are in the transition metal block, but do not act as transition metals. So silver, although a transition metal, will always be a +1. Zinc is the other one like it. Zinc will always be a +2, even though it's in the transition metal block. Likewise, there are two elements that are not transition metals, but act like transition metals. And those are tin. So tin, you have to specify. You have to use Roman numerals. And lead is the other one, Pb. For those, you have to use Roman numerals, even though they are not going to be transition metals. They can have several different charges. So going back to our problem with silver acetate, silver is a +1. Acetate is C2H3O2 with a negative charge. So the positive and the negative cancel out. It becomes AgC2H3O2. Then we have calcium cyanide. So calcium is a 2+, cyanide is a negative. So we put those together, we get CaCN. We need to use parentheses because we're adding a subscript to our polyatomic ion. And then our last one here is nitrous acid. So us means that it came from ite. So we have to think of what nitrite is. Well, we know that an acid is always going to have an H+, and then nitrite is NO2 minus. So those charges cancel, and nitrous acid would be HNO2. And that's how you name and write chemical formulas of simple ionic and covalent compounds for a general chemistry course.